Modern day mathematics grows increasingly complex on a daily basis. With new discoveries that further the frontiers of intellectual knowledge, mathematicians and scientists are making what was always thought impossible possible. Despite all this, most mathematicians always turn to the roots of mathematics to uncover hidden mysteries. Now, what are the roots of mathematics? Personally, I believe that mathematics has four founding pillars that lay a solid foundation to the knowledge of today. These pillars are algebra, number theory, trigonometry, and of course, calculus. The question that arises is, who was it that helped lay down these founding stones? The answer, of course, is not singular. There have been numerous stalwarts of the past that have dedicated their lives towards mathematics. The problem, however, is that the history of mathematics has not always been in the limelight, especially during the past millennia. Just look back at the 17th, 18th, and 19th centuries. With kingdoms, monarchs, conquests, and wars a priority, mathematics has unfortunately always been in the background. In addition, many people have been made to forget the people who actually made these discoveries. India, with its long reign of shifting conquerors, had been brought to its knees, and only recently have the marvels of ancient Indian mathematics started to resurface. Of course, this is not a history lesson, but it's of key importance to understand the works of a group of people who have been influential in developing mathematics as we know it today. So let's talk about them. Let's talk about the Kerala School of Mathematics. The Kerala School of Astronomy and Mathematics was a school founded by Madhava of Sangamagrama in Kerala, India. The school flourished between the 14th and the 16th centuries. In attempting to solve astronomical problems, they independently discovered a number of important mathematical concepts. Their most important work was series expansion for trigonometric functions and was described in Sanskrit verse in a book by Nilakantha called Tantra Sangraha, and again a commentary on this work called Tantra Sangraha Vakya of unknown authorship. The theorems were stated without proof, but proof for the series for sine, cosine, and inverse tangents were provided a century later by Jyeshadeva, another stalwart in ancient Indian mathematics. Their work, completed 2 centuries before the invention of calculus in Europe, provided what is now considered the first example of a power series. Alright, now that I've talked about the history of the Kerala School of Mathematics, let's understand what series really are. A series is just a sequence of numbers that are placed in a particular pattern. 1, 2, 3, 4, 5 is an example of a series. So is 2, 4, 6, 8, 10. An interesting one is 2, 4, 8, 16 and 32. This is also a series. But what separates them? A close look and you'd be able to see that in the first and second series, the difference between consecutive numbers, also called terms, is constant. In the example of 1, 2, 3, 4, 5, the common difference is 1. And in the example of 2, 4, 6, 8, 10, the common difference is 2. This is known as an arithmetic progression. An arithmetic progression or arithmetic sequence is a sequence of numbers such that the difference between consecutive terms is constant. However, the third example I used does not have a common difference. Between the first 2 terms, the difference is 2. Between the next 2, the difference is 4. Then 8, then 16, and so on. The difference keeps increasing. However, if we evaluate the ratio of one of the terms and its consecutive term, we see that the ratio always stays the same. Here, 4 by 2 is equal to 8 by 4, which is equal to 16 by 8, which is all equal to 2. Here the terms have something known as a common ratio. In mathematics, a geometric progression or a geometric series is a sequence of non-zero numbers such that each term after the first is found by multiplying the previous one by a fixed non-zero number that is called a common ratio. Now, in any geometric series, When the common ratio is less than 1, we have what is known as a convergent series. Here is an example. 27, 9, 3, 1 and so on. Look at the given example. The numbers don't seem to have a common difference. 9 minus 27 is not equal to 3 minus 9, which is not equal to 1 minus 3. So, this cannot be an arithmetic sequence. But upon dividing the numbers by their consecutive term, we can see that the common ratio is the same. 9 by 27 is equal to 3 upon 9 is equal to 1 upon 3 and so on. This gives us a common ratio of 1 by 3. As you can see in this illustration, the terms keep getting smaller and smaller. Herein develops what is known as a sum to infinity. For the explanation of the sum to infinity, we start by looking at the sum of a geometric series. The sum of a series is just the arithmetic sum of all the terms. So in the previous case, it would be 27 plus 9 plus 3 plus 1 and so on. The nth term for any geometric series is given by the formula g of n is equal to ar to the power of n minus 1, where a is the first term of the sequence, r is the common ratio, and n is the term to be found. To find the sum to n terms, we place these values on a single line up to the nth term, as shown. In the next line, we multiply both sides by the common ratio r and get the following sequence. Upon subtracting the above part from the lower one, we get the formula for the sum to n terms as a multiplied by 1 minus r to the power of n whole upon 1 minus r. Now, in the situation that modulus of r is less than 1, that is, minus 1 is less than r is less than 1, we have a sum to infinity. As n tends to infinity, r to the power of n tends to 0. This means that as n becomes a very large value, the value of r to the power of n becomes very small, such that it has negligible impact to the total sum. For example, when n is 90 million and r is 1 by 2, naturally the value of 1 by 2 raised to the power of 90 million will be very small. In the formula, it means that the sum becomes a multiplied by 1 minus 0 whole upon 1 minus r, and thus the sum to infinity is just a upon 1 minus r. Right. So, why did I explain this? It is often regarded that the discovery of such series was done only in the European world. For years, English scientist Isaac Newton and German philosopher Gottfried Leibniz both claimed credit for inventing the mathematical system that we know today, somewhere around the 17th century. However, the Kerala School of Mathematics identified the infinite series, one of the basic components of calculus, in 1350. Incredible, right? Dr. George Joseph, a member of the research team who carried out the study to uncover this discovery, said, "The beginnings of modern maths is usually seen as a European achievement, but the discoveries in medieval India between the 14th and the 16th centuries have been ignored or forgotten. The brilliance of Newton's work at the end of the 17th century stands undiminished, especially when it comes to the algorithms of calculus. But other names from the Kerala school, notably Madhava and Nilakantha, should stand shoulder to shoulder with him, as they discovered the other great component of calculus, the infinite series. But it doesn't stop here. Madhava also gave the infinite series for pi, which is the ratio of the circumference of a circle to its diameter. It is expressed in his writings as follows. The above phrase means the diameter, Vyasa, multiplied by 4 and divided by unity. Again, the products of the diameter and 4 are divided by odd numbers like 3 and 5, and the results are subtracted and added in order to the original result. So, in modern notation, pi by 4 is equal to 1 minus 1 by 3 plus 1 by 5 minus 1 by 7 and so on and so forth. This series is ascribed to Gregory and Leibniz in the 17th centuries, who came 3 centuries later. Madhava was not content with merely stating this momentous result, which is not a very effective way of calculating pi. The verse quoted above also goes on to give what are known as end correction terms that can be used to find a very accurate value of pi without using too many terms. Using only 50 terms and an appropriate end correction terms, Madhava found a value of pi that is very accurate. It is expressed in the following verse. The verse means, wise men say that if the diameter happens to be 9 into 10 raised to power 11 units, then the measure of the circumference of the circle is the following number. The first half of the verse expresses a number using the Bhuta Sankhya system, where each part of the phrase depicts a number as shown below. Vibudha equal to 33, Netra is equal to 2, Gaja is equal to 8, Ahi is equal to 8, Hutasana is equal to 3, Tri is equal to 3, Guna is equal to 3, Veda is equal to 4, Bha is equal to 27, Varana is equal to 8, and Bahu equals to 2. The value of pi is given by the above verse, and it comes to the following number divided by 9 into 10 raised to power 11, which gives us 3.1415926535592, which is correct to 11 decimal places. After researching this, my mind was left blown. There have also been arguments for the possible transmission of information from Kerala to the Western world, due to the fact that Kerala was in continuous contact with China, Arabia, and Europe. This suggests of some communication routes and chronology by some scholars. There have been many reasons why the contribution of the Kerala school has not been acknowledged. A prime reason is the neglect of scientific knowledge emanating from the non-European world, a legacy of European colonism and beyond. Of course, there are other factors at play too, such as the little knowledge of the medieval forms of the local language of Malayalam in which these texts are written. Regardless of all this, however, as we learn more and more about the works of our ancestors, it gives us a glimpse into the possibilities that lay before us. Again, I reiterate that these discoveries were only made possible because of keen observation. There have been other claims over the discoveries of the Kerala school of mathematics, such as the adoption of the heliocentric model of the solar system in 1500 AD, some 43 years before Nicholas Copernicus came up with his model. However, while this remains a disputed fact, we can't say that this discovery is set in stone. Only time will tell us if these claims stand true. If they do, they only further prove the ingenuity of our past mathematicians and astronomers. That's all for today's video. I hope you enjoyed the journey of learning about this incredible school whose discoveries to date stand shrouded in mystery and conspiracy. I will be increasing the frequency of video uploads, and so I hope you all are excited for that. As usual, please do remember to like, subscribe, and share this video. Until next time, thank you.